Welcome back. If you remember from the last video, I showed you how to do a between groups ANOVA in Excel. So today I'm going to show you how to do a within groups ANOVA in Excel. Now we're going to conduct a within groups ANOVA whenever we have a dependent samples design. In other words, we have a within groups design and we have more than two samples or two groups of data. An example of this might be if I wanted to implement an intervention to increase fruit and vegetable consumption in elementary students. I could get a baseline measure of their fruit and vegetable consumption. I could then get another measure during the intervention. And then I could get a third measure after the intervention to see if fruit and vegetable consumption has increased. So in that case, I would be taking every single one of my participants, the children in this case, and I'll be measuring them both before the intervention, during the intervention, and after the intervention. So every child would have 3 data points. So within groups ANOVA is also called a repeated measures ANOVA. Now that's different than what we did with the between groups ANOVA, because remember with the between groups ANOVA, each person was only measured once in only one of the levels of the independent variable. But now with the within groups ANOVA, we're going to be measuring each observation multiple times, once in every level of that independent variable. So we're going to have multiple measurements for each one of our observations. Now, because each of our observations are going to experience every level of that independent variable, we then need to be aware of the order of presentation. So we would prefer to have a random order when it comes to presentation. However, sometimes that's not possible. So again, with our example with before, during, and after some intervention, we can't randomize the order across time. So we can't say for one child that we're going to get an after the intervention measure, then get the intervention, and then do before the intervention. That doesn't make sense because we're bound by time. So sometimes we can't randomize the order of the levels of the independent variable. And of course, that comes at a disadvantage because now we might have an order effect. That what happened in the previous measurement, let's say at pre, influences what happens during, which may influence our measurement after. That's what we call an order effect. Now, the best way to minimize the error due to order effects is to randomize. So whenever possible, we try to do that. Just remember that sometimes that's not possible, just like in this particular example. Now, the distribution for within groups ANOVA is still the F distribution. And remember, that is a skewed distribution. It starts at 0 and it only goes in the positive direction. And of course, it goes in that positive direction for an infinity. The line never touches the x-axis. But you have seen that F distribution in the narrated PowerPoints already, and we demonstrated it with the last video as well. So let's go ahead and jump into an example. Let's do a within groups ANOVA together. You're going to find that very, very similar to what we did with the between groups ANOVA. We'll just make a few adjustments. It's going to feel a lot like review. All right, so hopefully you've had a chance to go ahead and open up that Excel spreadsheet as well as the directions document. We'll take a look at both of those when it comes to conducting our within groups ANOVA. Of course, we're always going to start with looking at our data file, trying to understand the variables that we have. And so notice here that we're going to have 3 columns of data. Each one of those columns will represent a level of the independent variable. So it looks like we have a column for friend, significant other, and parents. And so we've seen a couple of these levels before, significant other and parents, in a previous either assignment or video. Now we're going to add a third column. We're going to put in friend as well. So let's go ahead and go down to the code book here. Let's take a look at each one of these variables. So it looks like our friend level is the level of commitment towards your best friend. And if we hover over that label, we'll see that it's on a 1 to 10 scale, where 1 is would do nothing, they say, and 10 would do everything that they say. So the higher the values, the more likely they are to be committed to their best friend. The second level is the level of commitment towards your significant other. And then finally, that third level is commitment towards your parents. So let's take a look at our scenario so we know the context in which our statistical analysis is going to occur in. So it says, suppose you're interested in studying how other people can influence someone's behavior. You decide to set up a survey link on your Facebook page for your friends to access. You ask in the survey for each Facebook friend who chooses to do the study to indicate their level of commitment to her or his best friend, significant other, and then parents. Notice here that we're going to present this in a random order. And again, that random order is to minimize the error due to order effects. We don't want our previous question or image or prompt to influence how our participants respond with the other levels of that independent variable. And of course, that's going to increase our internal validity of the study. So commitment looks like it was measured on a 10-point scale. We talked about that already, where a 10 indicates a high level of commitment. And looks like we're going to use an alpha of 0.10 for our test or for our analysis here. So let's go back. Let's take a look at our data again in the data collection tab. If I just scroll through the values, you're going to see we have some missing values in there. We're going to want to deal with that. We'll have a little bit of setup when it comes to our within groups ANOVA. So let's take a look at our directions page. So very first thing is going to talk about setting up your data. So that data manipulation in this case is that we want to make sure that every observation, whether it's people or things, that every row has 3 measures in there or 3 values in it. So that's the very first thing that we're going to do. Because this is a repeated measures design, it is a within groups design, we need to make sure that every observation is being measured in every level of that independent variable. So any observations that does not have 3 measurements in it, we're going to want to delete, because Excel's not going to be able to use that data anyway for the analysis, and it's just going to give you an error. And so we're going to remove those observations that don't have 3 values in every row. So we'll do this as we've done it all semester long. We're going to sort each one of these columns. I'll start with column A, and I will sort that column. Again, doesn't matter if you do smallest to largest or largest to smallest. But once I sort it, I'm going to scroll down to the bottom. I'll look for any empty cells. It doesn't look like we have any with the friends column there. Let's take a look at the significant other. We'll sort that column. Scroll down, and you notice that we have 3 empty cells here. So that means we can't use any of these observations in these last 3 rows. So we're going to go ahead and delete them. Now, if you take a more advanced statistics class, then they'll teach you how to input data in there so that you don't lose those observations, but that's for a different class. So we're just going to highlight those 3, and we are going to delete them. And finally, we're going to do that 3rd column. And you'll see it looks like there's 2 more missing cells there, so we're going to delete those 2 cells as well. So remember that each one of our rows here represents a different participant, remember a different friend on our Facebook page. And so we always want to make sure that we're expanding the selection when we sort to keep those values all in the same row. And so the same person that gave us this 7 here for their commitment towards their friend is the same person that gave us this 7 for their commitment towards their significant other, which is the same person that gave us this value of 3 for their commitment towards their parents. Okay, so now that we've set up the data, let's take a look at what we need to do next. So it looks like we're going to go ahead and get our descriptive statistics for each level of our independent variable. That's the same step as it was for the between groups ANOVA. In fact, all of our tests up to this point, we want to get our descriptives for each one of our columns. And of course, you know how to do that already. You do not need to get your confidence level for the mean here. We won't use it in this particular example. Here's our first set of descriptives. Let's get the other 2. And then 1 more. Okay, so let's just glance at those really quick. Of course, what we're interested in here is the mean. We're interested in the standard deviation. We're also interested in the count. So in this case, we have a count of 39 when it comes to commitment towards friend. So this would tell us that it looks like we're meeting our normality assumption. Now that's going to be the same case for all 3 of them, because remember, you have to have 3 measurements for each one of your observations. So you're going to have equal sample sizes. So all 3 groups are going to have 39. It looks like we can say we meet that assumption of normality for the overall test. Now, just looking at our values here, it looks like for commitment, for friend, it's 6.44. Significant other is 7.41. And then for our parents, it is 7.72. And so there is some variation among the means. It looks like parents are being rated the highest, friends being rated the lowest here. But what we want to know is, are these differences at a greater than chance level? And the only way we're going to be able to find that out is to do our within groups ANOVA hypothesis test. So we have our descriptives. Let's go ahead and go to our directions page. We're going to go to step 2 here, and this is where we're going to get our ANOVA. So notice here that when we get the ANOVA, that we're going to use the 2-factor without replication option. So we'll go data analysis. We'll click on our ANOVA 2-factor without replication option. We'll click OK. We'll highlight our data, and notice here it says highlight only the data. Don't highlight the labels. Unfortunately, in Excel, there is a glitch that if you highlight the labels, that it won't give you the output. So only grab the data, don't grab the labels. Do not check the labels box because, again, we're only highlighting the data. We're not highlighting the labels. And then we'll put our output wherever we want. So let's get to our spreadsheet here. Let's go to data analysis. We have our ANOVA options right at the top of our drop-down menu. So we want the one 2-factor without replication. We'll click OK. We'll highlight our input, but remember, we're not going to grab the labels. We're only going to grab the data. So left click, hold, and highlight them. We will not check the labels box here, again, because we only have the values. We didn't highlight the labels. We do need to change our alpha. We're going to change that alpha to 0.10 as per the scenario. And then we're going to place that output just right next to our descriptive statistics. And then we'll take a look at the output. So there's our output. Let's take a look at it here really quick. You're going to notice that there's a whole lot of rows here. In fact, there's a row for every one of your observations. So within groups design, what's nice about it is that we can get an average for each person. So if row number 1 here is our very first person that's in our data set, very first participant, we know that we have 3 values, right? 7, 7, and 3. And so we can get a count. There's 3 values there. And the average of those 3 values is 5.67. What's nice about the fact that we can get averages for each one of our observations is that we can then use those averages to remove the variation due to the fact that people are different from each other. So remember, our individual differences increases variation. And so if I can treat everyone in my sample as if they're the same, then I can reduce the error and make it easier for me to reject the null hypothesis. And so that's what we see here. We get an average for every single person in our data set, and that's going to be for each of those rows. So I'm going to scroll down here. Once we get past the rows, we're going to go to the columns. And so the columns represent the levels of the independent variable. So column 1 here would be friend, or best friend. Column 2 would be the significant other. And column 3 would be parents. And so again, if we're looking at original data, right, column 1 is friend, column 2 is significant other, and column 3 is parents. So it's helpful to go ahead and relabel those in there. Remember, it's not going to do it automatically, so you're going to have to remember what they are, and so type it. So I would recommend go ahead and typing it in. All right, if you're looking at every single one of those particular groups, you're going to see that we have an average for each one of them. Now, again, you can scroll up and down to get your averages and your variances, but sometimes it's easier just to type it in so that you don't get confused later with it. Remember, also, you can always go back to your descriptives to get your standard deviations for each of your groups, but also remember that if you take the square root of the variances, that you will also get that standard deviation as well. So again, take it to the power of 0.5, and you'll see that those values will match your standard deviations that are in your descriptive statistics. Remember, you'll be asked to report your mean, standard deviations in your counts. And so if you didn't want to get your descriptives, you can get all that information here in your output. Your counts are this very first column here after your labels. And then your standard deviations you will have to calculate. And of course, the average or the means is provided as well. All right, so that's the summary table. Let's go ahead and go down to the ANOVA output here. So this is our source table. You're going to notice a few things that are different here when it comes to a within groups ANOVA from when we did a between groups ANOVA. First thing you're going to notice that there's a new row within the source table. And that's going to be this row that is labeled rows. In this case, remember, rows represents each one of our participants. So we're going to call this subjects. So you're going to note here that for whatever reason, Excel flips the order of subjects and between groups. So you need to make sure you remember that rows correspond to your subjects, to your participants, and columns corresponds to your levels of your independent variable. That's going to be flipped from what you learned in the narrated PowerPoint. So make sure you make that mental correction. Now, there's certain things that kind of gives it away. So if you're looking at that very first row, you're going to notice the degrees of freedom is 38. Well, that's just the number of observations minus 1. So we have 39 in each group, minus 1 is 38. So that's going to tell you as well that this is dealing with our participants, our subjects, not with our levels of our independent variable. And if you look at the columns row, you'll see that there is 2 degrees of freedom, which makes sense because we have 3 levels. And so 3 minus 1 will be 2. So I recommend relabeling your sources of variation to be subjects between your groups, and then error is just your within groups variation. Okay, so let's talk about what each of these rows are going to tell us. So when we get an F statistic for our subjects line, that is testing whether or not our participants are different from each other. Now, we're not particularly interested in that here because we want to know the commitment levels between friends, significant others, and parents, not if our friends on our Facebook page differ from each other. So even though we have that row there, the only reason we have it is to remove the variation due to the fact that people are different from each other. In other words, we would remove the sum of squares for subjects when calculating our hypothesis test and also the effect size. What we are particularly interested in is the row for between our groups. Remember, our groups are the levels of the independent variable. So this is the row that I'm going to highlight here. This is the one that we're going to want to take a look at here in a few minutes. And then within is still the error variation. It is what is left over once you account for the levels of the independent variable and the variation due to your individual participants. Now, mathematically, how we get the between groups variation as well as the total variation is exactly the same as it was with the between groups ANOVA. And so these sum of square values use exactly the same formulas. But the ones that are different are subjects and within. And so we should talk about those just briefly so you understand conceptually what's happening behind the scenes with the math. And so for subjects, the formula is sum of squares for subjects equals the mean of each subject or participant minus the grand mean squared. So remember your squared value squared, then summed together multiplied by K. In this case, K is the number of groups. So if you remember, I mentioned earlier that if we look at the summary table, that for each one of our participants, we can get an average. In this case, for the first one, it's 5.67. And so if I wanted to calculate the sum of squares for subjects by hand, I would take each one of these averages and I would subtract the overall mean for all of the values in my data set. I would square each of those, add them all up, and then multiply by the number of levels or the number of groups in my study. In this case, we would have 3, right? So 3 levels of the independent variable. We have for our best friends, significant others, and then also for parents. And that's how we would calculate the sum of squares for subjects. Now, calculating the within group sum of squares is a little bit more challenging because of the additional row for subjects. And so I always recommend, if you were to do your calculations by hand, I would always recommend to use subtraction. And once you know the total sum of squares, the subject sum of squares, and the between sum of squares, you can just take your total sum of squares minus subjects minus between, and that would give you your within sums of squares. But if you wanted to calculate it by hand, there is a formula for it. And that formula is quite long. It would be the sum of squares within, and it would equal every single one of our original values. So each X value in our data set minus the mean for the participant minus the mean for the group. In this case, we might call it X plus the grand mean. I would then square that value, and I would do that for every single one of my observations. So in this case, we have 117 observations. So I would do that 117 times, once for every single one of the observations, subtracting its corresponding mean for the participant, minus its mean for the group that it's in, or the level of the independent variable that it's in, plus the grand mean, squaring it, and then I would add all 117 of those squared values up, and that would give you my sum of squares within. So you can imagine, after doing 117 of those, right, the chances of making a careless error someplace in there is going to be pretty high. And so thank goodness that we have statistical packages that does those calculations for us in a matter of a fraction of a second. But again, the whole purpose of me showing you those formulas is just so you have an idea of where we're getting those numbers from. It's not magic. There is a mathematical formula behind it. Essentially, what we're saying with our sum of squares is that people differ when it comes to their commitment level to others. That also the type of other matters, so whether it's a best friend, significant other, or parent. That we know that across all three of our groups that our values differ from each other, so we get a measure of those differences in squared units. And then finally, the within is everything that is left over that's not accounted for by individual differences or a subjects line, or by the levels of that independent variable. So in this case, our best friend, significant other, or parents. So what we're particularly interested in are the variances. So remember that the F statistic is the variance between divided by the variance within. And so the F statistic is an analysis of variance. And so what we're particularly interested in here are these values. The MS, the mean squared, are the variances. And to get those variances, we just take our sum of squares and we divide by our degrees of freedom. So we take 34.94, divide by 2, we get 17.47. And we take our within sum of squares, divide by within degrees of freedom, and we get 1.67. Once we have those two values, we can divide them, and that's going to give us this 10.45 value, and that's the F statistic. Now, we always need to compare that F statistic to something, so we're going to compare it to the F critical value. Now, remember, again, we're not interested in the F statistic for subjects because we don't really care so much that people differ. We know people differ to some degree, whether it's significant or not. That's not our purpose of this research. For this particular research question, we want to know the levels of our independent variable. So commitment to friends, commitment to significant others, commitment to parents, do those differ? And we're going to find that in that betweens row in our source table. So let's draw out our F distribution. It is a skewed distribution. It is a positive distribution. It starts at 0 and it goes to infinity. At some point on this distribution, we're going to have a critical region. In this case, it's going to represent 10% of the population because we set our alpha at 0.1. And it looks like that F critical value is going to be 2.37, and that's going to be a positive value because F statistics and F critical values are always positive. So then we're going to compare the F statistic of 10.54 that will exceed 2.37 someplace out here, right? 10.45. And so it looks like we're going to reject the null hypothesis. Now, if that F statistic fell between 0 and 2.37, we would fail to reject the null hypothesis. But it looks like in this case, there's at least one difference among our comparisons between friends and significant other, friends and parents, and significant others and parents. Remember, we have 3 different comparisons here, which is why we're doing that F statistic test. So it looks like based on the hypothesis test, we do have some differences at the group level. Now, again, we don't know exactly where those differences are. That's why we'll have to do a post hoc test a little bit later. But before we get there, let's go ahead and let's get the effect size for our particular study. So remember, the effect size is different than the hypothesis test. And so you always want to make sure you verbalize this in your responses when you talk about the effect size, is because the hypothesis test is at the group level. The effect size is at the individual level. So we know based on the hypothesis test that there's at least one difference among our comparisons between friends, significant other, and parents. What we want to know is, on average, what does this mean for an individual such as myself? Am I more likely to be committed to my best friend or significant other or parent as an individual? And so remember, we can reject the null hypothesis and not find anything at the individual level. We can fail to reject the null hypothesis, not find anything at the group level, but find something at the individual level. So you always want to make sure you look at your hypothesis test results as well as your effect size. So let's take a look at our directions page. So notice we have our effect size down here, and notice that the formulas changed a little bit from the last video. So remember in the last video with the between groups ANOVA, we just took the sum of squares between and we divided by the sum of squares total. But remember here, because we have a within groups design, because we're measuring each participant multiple times, we can actually remove the variation due to people being different from each other. And that's what you see here in the bottom of this formula. So we're going to subtract the sum of squares for subjects. In other words, we're going to remove the fact that people differ from each other, the participant variation, from the overall variation in our study. And what that's going to do is it's going to isolate. So what that's going to do is going to treat everyone as if they're the same statistically. Now, even though we know people differ, we're trying to remove that variation so we can get a clearer image of what we're really interested in, and that's the commitment levels for friends, significant others, and parents. So your commitment level to your parents may differ from my commitment level to my parents, but I want to keep that constant so I can get at the overall differences among my levels of the independent variable. Okay, so let's go to our spreadsheet. Let's get that effect size. I'm just going to type effect size down here underneath my source table. I'll hit equals, click on my sum of squares for between. Now make sure you're clicking on the between group sum of squares here because our table shifted a little bit from what you learned in the narrated PowerPoint. So in this case, between is 34.94. We're going to divide that, and don't forget your open parentheses, by the sum of squares total, so 261.86, minus the sum of squares for our subjects. So again, we're going to remove the fact that people differ from each other. We're going to treat them as if they're the same mathematically when it comes to commitment levels. And then we're going to hit enter. And it looks like we're going to get an effect size of 0.22. Now remember your conventions for ANOVA. So around 0 is going to be no effect. Around 0.01 is a small effect. Around 0.06 is a moderate or medium effect. And around 0.14 is a large effect. So this looks like it's going to be a large effect. 0.22 is going to be a lot closer to our large category of 0.14 than it will be to the other three categories. If you were to write this up, remember that the effect size is a ratio, so we can talk about it in terms of percents. And so if we have 0.22, so what we're saying is that it appears that 22% of the variation in people's levels of commitment can be accounted for by whether the person is a best friend, significant other, or parent. Now note we're going to add one thing to this explanation. Because we subtracted the sum of squares for subjects, we're also going to add at the very end when individual differences are removed. So it looks like about 22% of the variation in people's commitments to others depends on whether those others are a best friend, significant other, or parent when individual differences are removed. And of course, this is a large effect. So that's our interpretation for the effect size. Now remember with our hypothesis test, we did reject the null hypothesis. That told us there's at least one difference among our comparisons, but we don't know exactly which comparison is significant. So we need to do what's called post hoc tests. So let's go to our directions page, have our effect size. We talked about its explanation. Let's go down to our post hoc tests. Now again, we're going to be using a Q test. And so notice that our formula is exactly the same as it was a between groups ANOVA. We're still going to take the means of two of our groups, compared to each other, divided by a standard error pooled. But notice that our formula for that standard error pooled is a little bit different. We're still going to take that mean squared within, but instead of dividing by the harmonic mean, we're going to divide by lowercase n. So lowercase n is the number of observations in one of our groups. Up to this point, you've been familiarized with a capital N. A capital N is the total number of observations in your data set, regardless of the number of groups. So just note here that the lowercase n is not all the values in your data set. It's just the values in one of your samples or in one of your groups. But everything else about that formula is the same. In fact, if you were to use the harmonic mean in the denominator, so remember back from between groups ANOVA, we calculated the harmonic mean. If you use that harmonic mean, then you would get exactly the same value as lowercase n. So if it's easier for you just to do the harmonic mean for both the between and within groups ANOVA, then go ahead and do that. You'll give yourself a little bit more work, but you'll get the same answer. Okay, so let's go to our spreadsheet. We need to calculate the standard error pooled. We also then need to get our post hoc tests. That means we identify our comparisons. So in this case, we're going to have 3 comparisons. We're going to compare friend versus significant other, friend versus parents, and significant other versus parents. So we're going to get a Q statistic for each one of those comparisons. But first we need to get this standard error. So again, that formula is equals. I'll do an open parentheses. I'll go up to my mean squared within. So that's that value of 1.67. So make sure you're clicking on the mean squared within. That's what our formula is asking for. And we're going to divide by the number of observations in one of our groups. I'm just going to scroll up here. Remember, here's our counts for each of our groups. I'm just going to click on one of them. Doesn't matter which one, because remember, they're going to be the same. Your sample sizes are going to be the same if you're doing a within groups ANOVA. And then I'll close my parentheses. Then I want to take the square root of that value. So I'll get my up arrow for the power symbol, and then 0.5 for the square root, and then I'll hit enter. And so it looks like our standard error in this case is 0.21. So we'll use that standard error for all of our calculations for those Q statistics. All right, so let's go ahead and calculate our Q statistics for each of our comparisons. Remember that formula is the means of 2 of our groups at a time divided by the standard error that we just calculated. So for our first one, for friend versus significant other, I'm going to hit equals. And then we're going to subtract the means of those 2 groups from each other. Remember, here's our averages. I'll take our average for friend, and I'll subtract our average for significant other. Close parentheses. And I'm going to divide by the standard error. I'll hit enter. And it looks like I get negative 4.71. I'll do the same thing for comparing friend versus parents. So I need to get my means, subtract them from each other. Don't forget to put that in parentheses. And then I'm going to divide again by that standard error of 0.21. And looks like I get negative 6.19. Okay, so we have one more comparison here. Grab my 2 means, except now it's going to be between significant other and parents. So I'll subtract those 2 from each other. Divide by that standard error, and I'll hit enter again. It looks like I get negative 1.49. So that gives me all of my Q statistics for each one of those individual post hoc tests. I now need to determine whether I'm going to reject or fail to reject the null for each one of those comparisons. So that means I need to get a Q critical value. Remember, every hypothesis test has a statistic and it has a critical value that you compare to. So whether it's Z or T or F or Q, we're always going to compare to a critical value. Now notice that we don't get that critical value here in Excel, so we'll have to look that up on a table. And so remember, you can find that table in the back of your textbook, or you can find it in the link on the course webpage. All right, so let's go to that table. Remember, in this table, we have columns and we have some rows here. Our columns going across the top is the number of treatment levels. That is the number of independent variable levels. Here we have 3, friend, significant other, and parent. So we're going to look in the 3 column. On the far left, you're going to have your within groups degrees of freedom. To find your within groups degrees of freedom, just go to your source table, look for your degrees of freedom column, and within, it looks like we have 76. So we'll use that value to find our critical values in our Q table. You're going to notice that the table in the back of your book is not going to have an alpha of 0.10. That's okay. The principles will be the same, and I'll provide a different table. We end up using an alpha of 0.1 when it comes to an assignment or an exam. So we would scroll down until we get to our value closest to 76 here. So notice 76 will be closest to 60 on this particular table. We then look at our alpha or our significance level for that. But because it's not shown in this particular table here, I'll show you on another table, but it works exactly the same way. So across the top is still our groups. So we still have 3 for our levels of our independent variable. Our degrees of freedom will be down the side here. And then these tables here are for an alpha of 0.10. So if we end up using an alpha 0.10 on any example, I will provide these tables as well. But if we're to look here and look down our degrees of freedom, we'll see that we don't have 76, but we do have 60 and 80. And in this particular case, it would be closer to 80 than it would be to 60. It looks like in this particular table that our critical value is going to be plus or minus 2.95. Remember, it's plus and minus because the Q distribution is always two-tailed. So regardless of which table you use, you should be able to get a Q critical value. So in this case, that Q critical value is going to be plus and minus 2.95. So now that I have that critical value, I can compare each one of my test statistics to that critical value to determine whether I'm going to reject or fail to reject the null hypothesis. So I'm going to draw out our distribution. Again, it's a normal distribution. We're going to put critical regions in each tail of this distribution. It'll be negative 2.95 and 2.95. The Q distribution is always centered at 0, a Q of 0. And so now we can compare each one of these Q statistics. So for our very first comparison between friend and significant other, we get a Q statistic of negative 4.71. That's going to be someplace over here, 4.71. Now note that is a negative value, so that's saying that one of the groups has a lower mean than the other group. So we can take a look here and see which of those is rated as lower just by taking a look at the means. And so if my mean for friend is 6.44 and my mean for significant other is 7.41, so it looks like there's a lower commitment level for friend or best friend than it is for a significant other. So I can write that out in my explanation. So friend versus significant other, it looks like we would reject the null hypothesis. It appears that commitment to a best friend is lower or less than commitment to a significant other. So again, remember when you're talking about your statistical decisions for each of your post-hoc tests, make sure you indicate whether to reject or fail to reject a null hypothesis, and then generally say what that means in relation to the sign that you have with your Q statistic. All right, so if we're looking at friend versus parents, so best friend versus parents, who are we more committed to? We'll see that we get a Q statistic of negative 6.19. That falls even more extreme on our distribution, again, where we would reject the null hypothesis. Remember, in the tails, we reject the null. In the center, we fail to reject. So I can write that out. Again, this negative value tells me something. It tells me that one of the groups is lower than the other when it comes to the means. If we look at those averages again, we see that parents are rated higher. So that means friends have a lower level commitment compared to parents. So again, we would reject the null hypothesis. And it looks like in this case, it appears that commitment to a best friend is lower than commitment to, and I'm just going to change it to say parents. And there's our conclusion. All right, so one more. It looks like we're going to compare our significant others to our parents. So is our commitment level different between those two particular levels of the independent variable? we get a Q statistic of negative 1.49. So negative 1.49 does not exceed our critical value. It falls in this region where we will fail to reject the null hypothesis. Negative 1.49. So for our statistical decision here, we'll say fail to reject the null. It appears that people's commitment level to significant others and parents are the same. So in other words, there's no difference between those two. And those are our statistical decisions for the post hoc test. So to recap with our particular analysis here, we found with the overall F-test with the hypothesis test that there was at least one difference among our groups when it comes to commitment level. When we looked at our post hoc test, we found that it looks like that our best friends are rated as having a lower commitment than for significant others and parents, but it doesn't look like significant others or parents are any different from each other. So it looks like we're just as committed to those two groups. We also found an effect size of 0.22. That was a large effect, so that told us that this not only applies at the group level, it also applies for the individual, such as myself or such as yourself. So remember that effect size gives you a little bit different information than just the hypothesis test by itself, and so make sure you make that clear in your write-ups and in your practical decisions. All right, so that's it for a within groups ANOVA. Please remember to upload your spreadsheet with your name as the file and submit it below.